Assalamu alaikum. Welcome to lecture 22 of data mining. So I hope all of you are doing well. So we will continue with our discussion on outlier analysis and wrap it up most likely today. And then we will start talking about classification. And I will provide an overview of classification and discuss maybe one or two classification techniques in bit more detail, especially decision trees and random forest. So that would be the agenda for today and maybe also next lecture. I think we will probably start classification today and then it will continue till next lecture. So that is the plan for today. So are there any questions before I get started? So I think before I get into the second outlier detection technique, which is actually the last one that we are going to discuss, which is based on autoencoder, let me revise LOF, local outlier factor, which we concluded with last time. So local outlier factor, as we mentioned last time, is a proximity based approach, and all proximity based approaches rely upon some notion of similarity or distance or proximity in general. And this particular approach is based on the idea of the k nearest neighbors. And as such, it is kind of adaptive to the distribution of density in the data set. So that's why this is called local. So in other words, it detects an outlier based on the density that is seen around that point. So if that point lies in a sparse region, then it will only become an outlier if its neighbors are also even sparser. So, and sparser than that. And if the point is in a reasonably dense region, then it will only be an outlier if those in its neighborhood are less denser or sparser. So it's kind of relative, and to quantify this, it goes through a number of steps by looking at the object, looking at the objects around it and the neighbors around those objects, and then define a function, define a value which varies between -1 and 1. A value which varies, it basically is 0 and higher, and 1 means that not an outlier, or equal, and greater than 1 would mean an outlier. So very quickly, let me go over the equations again. Are there any questions on LO, by the way? So we need K as an input, okay, which is the number of neighbors in the neighborhood. So based on K, we find the K distance of any object in consideration, let's say object A. So this is the distance to the nearest, or not the nearest, the kth neighbor. So if K is 3, we find the distance to the third closest point to A, and that distance is called the K distance. And that basically forms the radius around the object A, radius in some hyperspace, depending on how A is represented, around A, and that defines the neighborhood around A. And all the objects in the neighborhood of A is defined by the set A. The set of objects in neighborhood of A. All right. And as we mentioned before, the number of objects in the neighborhood of A may be greater than K, for the reason that there might be multiple objects at the same distance from K. the kth object, there might be multiple kth distant object from A. Okay. So, and then after this, they talk about a concept called reachability distance, or you can say RD. Okay. So RD of A from some other object B. Okay. So this is given as max of the k distance of B, which is another object. Okay. Or the actual distance between A and B, whichever is maximum. So this is kind of a, you can say, quantization technique, and it's primarily meant to make sure that the results are more robust, there's less variation. The quantization, of course, is that if A lies in the neighborhood of B, then it's wherever it is in the neighborhood of B, its distance, its reachability distance would always be the k distance of B. But if A is outside the neighborhood of B, then its distance would be the actual distance, which is D, A, and B. So from this, then we compute the density of the region around A, which we call the local reachability density. Okay. So this is actually the inverse of the average density of the objects in the neighborhood of A. So basically sum, and this sum is over all the objects B in the neighborhood of A. Okay. This sum is for all objects B in the neighborhood of A. And the formula is, of course, inverse 1 upar aayega, and then there is a density in the denominator. Okay. And what is the density? That is basically the reachability distance A, B, okay, and of course divided by the number of objects in the neighborhood of A, N, A. Backslash. Okay. So this gives us the local reachability density of the object A. Okay. And from here, we get the final value. And the final value, of course, is based on the reachability density of the neighbors and the reachability density of A. And of course, that's actually average of that, the ratio. So LOF of A is basically then 1 divided by N A, which is, of course, the count of objects in the neighbor, then same sum over B in N A. And then we have this ratio of LRD of LRD of B divided by LRD of A. Okay, so this is a ratio for all objects B in the neighborhood of A. And then, of course, this is a sum. So we normalize the sum by the number of objects B in the neighborhood of A. So this value would be 1, of course, when the density, local reachability density of every neighbor in the neighborhood of A is equal to that of A, which of course means that A is not likely going to be an outlier. But if this LOF is greater than 1, then A is likely an outlier. Again, based on what? Based on the density of objects in the neighborhood of A. Okay. And of course, to actually find those objects, you might have to threshold this. So we have to threshold LOF to find the set of outliers in A. Okay. So of course, that threshold you will have, the domain expert would have to decide. But more importantly, this is a ranked value. So it's a score. So you can always look at the score from the top and just decide where you want to cut off. Okay. So you can do a bit of visualization and kind of interactive approach अडॉप्ट करके इसको डिसाइड कर सकते हैं. So this was the LOF technique, which, as I said, is based on proximity and uses the K nearest neighbor concept, considers local density of objects, and as such, it can handle objects, can handle data sets with varying densities. And as such, also, it is less prone to parameters. The parameter here, of course, is the K. So this is as opposed to the distance-based outlier approach that we looked at last time. That particular approach is more sensitive to the parameters, and it also is a global kind of approach, which finds which sets parameters globally for the entire data set, not locally, depending on the density. Okay, are there any questions here before I move on? Okay, so now let's move on to another approach. This approach actually, category-wise, it is called a reconstruction based approaches. But the most popular technique in this is the neural network based auto encoder, you can say outlier detection. Okay. But the principle that it uses is the principle of reconstruction. So let's go through this idea step by step. So what do we have at the start? Obviously, we have objects in some representation, vectorial representation. So we have objects X, which are represented in some vector space. And from this set of objects, we would like to find outliers, right? So that is the idea in clustering, also, as well as in outlier analysis. In clustering, of course, we want to group some of these objects into different groups. Okay. So an autoencoder is actually a neural network, and it's a neural network, and a neural network obviously has an input and has an output. Okay. And in general, whenever we have a neural network, we say that output is X and the corresponding, input is X and the corresponding output is Y. Okay, na? And there is obviously a non-linear mapping going from X to Y. So that is what a standard neural network is, or it does most of the time. And that mapping, of course, has some set of parameters. We'll go into that shortly. And those parameters are basically fixed by determining or comparing the value of Y that is outputted by the model and comparing with actual value. So it's kind of supervised learning. Okay? If there is a greater error, then there's going to be greater update in the model. All right. So, but in the autoencoder, the input and output are actually the same. So we input, for example, X as the input, which is a vector representing an object. It goes through some nonlinear transformations. And at the end, we also reconstruct that output, that input. And let's say the output of the network is X prime. Okay? Of course, this is the output of the network. And of course, we do know the true output. The true output is X. Okay? So we have transformed X through some processes and then reconstructed X. Obviously, during this process, there is going to be some errors. The output that we get is X prime. The actual output should be Y. So we do know the actual output, and we have the output from the network, so we can compute the error. So using this error, we can learn the model, just like we can learn the model in the standard neural network where we have a Y as well as the true Y. Okay? So that is why this is called auto, meaning that we are trying to learn the same thing. And why it is an encoder? Because this transformation from X to X prime goes through some coding. So usually, let's say X is a vector. So it's a vector of length, let's say ऊपर n दे दिया था m, ठीक है? So this m vector is coded to or is embedded into some lower dimensional space to a length of, let's say m कहा था मैंने, तो इसको मैं let's say I don't know, L कह दें, L, which is going to be less than m. So this is the coding, and then once we have the coding, we reconstruct the output again. Okay? So then, of course, so then decoded back to length m, which is the original input. Okay? So now let's look at the details of the structure. So usually X is the feature vector, and I mentioned this, I think, a few lectures back as well. One of the advantages of using a neural network is you can create a feature vector which has attributes of mixed types. So you can have categorical attributes, numeric attributes, and discrete attributes combined in one vector. So if you have a discrete attribute, you can use one hot encoding to convert it into a vector of 0 and 1 and put it into the vector X. Okay? Obviously, neural networks can only process numbers, so you need to have X to always have numbers. Okay, so you can handle mixed attribute types, and also you can handle large, high-dimensional vectors. Neural networks are good at processing high-dimensional vectors. So usually the processing in the network is something like this. Let's say we have a single hidden layer. And let's say that hidden layer has dimension L. Okay? So input layer, of course, has dimension M. Okay? And then we have output, which has dimension M again. Of course, you can have more hidden layers, but essentially the process remains the same. So let's say the weight matrix from input to hidden is W1. Okay? And I'll mention a dimension shortly. And from hidden to output is W2. Okay? So the processing, so output of hidden layer, which is the coded vector, let's say that is A. So this A is basically some function G of W1 into X, plus there is also a bias vector, let's say that is B1. So, okay? So this is the processing. A is then the coding for the vector X. Of course, there are parameters here, W1 and B1, which are learned during training. But I'm mentioning that, let's say you have some value, you can output A. So what is the size of W1? W1 is a matrix, of course. And iska size jo hoga wo hidden layer size hai L, और input their size है m. Because only then would this multiply with x to give you a vector of size L. And जो B1 है, this is a vector of length L. So, which means that A is a length L as well. So, A is thus the encoding or coded version of X. Okay? And the function G is an activation function, a nonlinear activation function, and usually it is the tangent hyperbolic. The tangent hyperbolic is an S-shaped function from +1 to -1. Okay? It's a smooth function from +1 to -1. So in other words, and this applies to each element of its argument. So in other words, जो आपका A है, उसमें सारी values होंगी. It's a vector. All values would lie between -1 and 1. ठीक है? So normalized हो जाएंगे between this range. So this is the coded version, but we need to decode it as well. So now the next step is हमारा जो output है x prime is the same, let's say function g. Same function भी ले सकते हैं या linear होता है. Typically, let's use another name, f. Then w2 into a plus b2. ठीक है? So this is the second, and this is a decoder part. The first is encoder part. The second is a decoder part, and we are getting back x prime. तो इसमें अब dimensions क्या है? w2 again is a matrix. So इसकी जो output है, it's of m. ठीक है? And then of course is L. So we are multiplying it with A. A is a vector of size L. So B2 is a vector of size M. Output है हमारी. ठीक है? And then F is an activation function, usually is linear. ठीक है? Actually, I think I'm not too sure. It's probably not linear. It's again, I think, linear to regression होगा ना. We are trying to map to the same thing. Non-linearity इसमें वहीं बीच में ही आ रही है. ठीक है, I think linear is fine. Yeah, regression problem है. Linear. ठीक है? So now we have our x and x prime, and of course you have a training data set. Multiple आपके पास x's होंगे, जो भी आपका data set है, जिसका आपने outliers निकालने, multiple होंगे इसमें. So to fix those parameters कौन से हैं? w1, w2, b1, b2. These are the parameters. These parameters need to be learned or fixed from the data. And what is the data? Data that I mentioned earlier, the whole set xi. Okay, this is our data. So how do you learn this? You minimize at the end, the output, you minimize a loss function. And loss function is usually the mean squared error between x prime and x. Usually, of course, sometimes you can also use the mean absolute error is also used. Okay? So this is an optimization problem, but this optimization problem is solved using a gradient descent approach and iterative approach, for which then updates the parameters w and b. So once you have learned this, let's say आपका model learn हो गया, so all these parameters are fixed. ठीक है? Any questions so far? Okay, so what have we done so far? We have a simple neural network input, one hidden layer, and output. The hidden layer has L units, which is going to be much less than M. So input is M, output is M, because we are doing auto, you can say, learning. So we are putting in X, and we are again regenerating X, which we call X prime. And it goes through some encoding, some embeddings, which is of smaller dimensions. Okay? So of course, in this transformation, which is nonlinear through the hidden layer, we have some parameters, W's, which are matrices, and B, which are vectors. How do you learn those vectors? We minimize, or we solve it. We learn them by minimizing a loss function. Loss function is basically trying to ensure that the distance, the sum of squared error or the mean squared error between X and S prime is as small as possible. The mean squared error basically is over a data set is simply, so if you write it in terms of, so हमारे पास data set कितना है, 1 over n है, of course this is the mean, ठीक है, then you have the sum for all I, ठीक है, so mean squared error vector form में मैं इसको लिखूंगा तो फिर ये बनेगा squared error, तो ये x minus x prime, so let's say ये vectors है, ठीक है, तो इसका फिर ट्रांसपोज करेंगे हम, so that it becomes row vector, dot product लेना है हमने, फिर then x minus x prime. So this is the mean squared error. This is of course the loss function which we try to minimize. So unconstrained optimization problem है, x prime compute करने के लिए सारे parameters w use होते हैं. While minimizing this, we find the best values for w's and b. ठीक है? Okay, now ये network आपका train हो गया. Let's say your network is trained, all the w's and b are fixed. So what happens now? Now it's the actual task of outlier detection. ठीक है? So वही data set है, the same data set which you used to train. Now you pass it through the network again, of course using those fixed w's and b. Pass it through the network का मतलब ये है कि वही आपने steps करने हैं. You compute A is equal to G W1 into X plus B1, ठीक है. उसके बाद फिर आपने X prime निकालना है, F into W2 into A plus B2, ठीक है ना. For each network, ठीक है. Sorry, for each input. Now, of course, this X prime is a reconstructed form of X. The reconstructed form of X. So now we check how far away this X prime is from X. Given our model is what? The network that we have learned. And if this reconstructed form is very far away from the model, then that object is likely to be an outlier. Because whenever you are building a model from this data set, whenever you build a model, the model would tend to learn the core normal behavior of the data. Remember, outlier detection is normal behavior, abnormal behavior. Here we are learning the normal behavior because that is the majority behavior. So majority behavior is learned by the network. Anything that is not following or significantly deviating from this majority behavior would have a significant deviation between the actual value and the output of this model. So that deviation would signify it to be an outlier. So in other words, we compute the, what we can say, the squared error between the X and X primes, which is also the इसका square root ले लें तो L2 norm भी बन जाएगा. You can say the L2 norm between, which is the length between X and X prime. ठीक है? So if you write this in terms of notation, L2 norm हम दो बार से denote करते हैं, X minus X prime So this is the L2 norm, which is actually the sum of squared error with the square root. Root means square error कह लें, mean नहीं हो रहा, root square error या Euclidean distance कह लें. L2 norm is equal to the Euclidean distance. ठीक है, square root भी ले रहे हैं. So the Euclidean distance between x and x prime, if this is greater than some threshold, let's say theta, then x is an outlier. Of course, theta is a parameter. So we pass all the objects x through the trained autoencoder, and for each x we'll get its corresponding reconstructed vector x prime. We then compute the distance, Euclidean distance or L2 norm between x and x prime. If that distance is greater than some threshold which we can decide, then we can call this to be an outlier. Of course, again here we do have a score. x2 minus x, L2 norm is a score है. Score को हम ranking कर सकते हैं, जैसे LOF में किया था. So ranking करके आप visualize करके देख लें कि कौन से कहाँ आपने cut off करना है. ठीक है, so this essentially is the autoencoder approach to outlier detection, which is a reconstruction based approach. We build a model over the data, and that model would obviously, since we are reconstructing or training it for reconstruction, it will try to capture the main behaviors within that data, because then the reconstruction error will be small. Once the network is trained, we basically then apply or send or feed forward each object, get its reconstructed output, and then based on the distance between the two, we can rank the objects, and we can cut off that, or we can use a cutoff on this rank to determine the outliers. So this approach has become more popular in recent years in the industry. The reasons for that is, as I mentioned before as well, the mixed attribute types can be handled easily. Okay, so it can work with high dimensional data, and you have a whole arsenal of techniques and you can say tweaks from the neural network domain that you can apply. So the network that I showed you was a simple network, simple feed forward network, but the essential architecture was what? You had an encoder and then you had a decoder. Okay? In our case, our encoder was a simple single layer. But depending on your problem, you can have different types of encoders and different types of decoders. You can have, for example, if your data set is sequential, you can use a sequential neural network for encoding. You can use a sequential neural network for decoding. If your data set is image, maybe you can use a convolutional neural network. So you have a lot of flexibility. Of course, you can increase the number of layers, especially when you have very high dimensions. Maybe you can have multiple hidden layers. So you have input, so hidden layer 1, then maybe hidden layer 2, and then hidden layer 3, and then you go in the reverse direction. Again, you will have, or maybe these are the only ones output. So in other words, the hidden layer 2 जो होगा, this would be the smallest layer. So आपके पास M था originally. So M था, let's say M is, let's say 1000. उसके बाद जो आप कह लें कि L1 आप कह लें, let's say 500 पे आ गए, L2 आप let's say 250 पे आ गए, फिर बाकी L3 फिर से आप 500 पे आ गए, and then of course m आखिर में 1000. ठीक है? Of course, as you have a deeper network, you'll have more parameters to learn. But the idea would be that it would maybe kind of learn the finer details of your data in a better way, especially if you have a lot of data. Thoda data hai to then of course you can run into problems, overfitting का problem हो सकता है. But if you have a lot of data, then you can have a deeper network. And of course, depending on the type of data, the encoder and decoder could be different. So far, we have used a simple feed-forward encoder, simple feed-forward decoder. You can use recurrent, you can use convolutional, you can use combinations of those as well. So any questions? Okay, any questions? Okay, so that was, I think, pretty much all regarding outlier detection. So we are focused primarily on unsupervised techniques, because previously we had only studied unsupervised techniques, which is clustering. And most these techniques that I studied, LOF, autoencoder, and distance-based outliers, are all unsupervised, and they are very similar to the techniques that we studied while we were studying clustering. Okay? But as we mentioned at the start, you can also have supervised approaches for outlier detection as well. So the next main topic that I wanted to cover, of course, in a bit brief way, is supervised learning and classification in particular. So, so any question on outliers before I move on? One of the challenges in outlier detection is that it's very application dependent, domain dependent. So of course we have studied some techniques here, but usually finding the threshold and tuning those techniques would be dependent on the application. And of course domain knowledge would be required quite a bit to set the thresholds and so on. So this is kind of crucial for this. Otherwise, you will run into too many false positives, and the whole idea of detecting outliers would fail actually. All right. So let's now talk about classification. So previously we had talked about clustering, which is a main task in data mining. So classification is another main task in data mining. And from a machine learning perspective, this is often categorized as supervised learning. Okay? So the idea in classification is that we learn a model in general, and or learn a procedure or build a procedure. And once we have that model, we can use that model to make predictions. Predictions basically means that given some new observations, some new examples, we can get labels or classifications for that. So let's basically take a simple hypothetical example. So let's say you have student data, and of, let's say, how student performs in the previous courses. And then based on, of course, the student data would have some features. So, and then based on that, we want to predict or determine what grade a particular student will get in the current semester course. Okay? So the previous information is from the previous semesters, and based on that, we want to predict. So in this case, हमारे पास data set क्या है? You have xi, which is student information. Xi in general would be a feature. It would be a vector, attribute value pairs, many of them. But for each of those student I, we also have some previously labeled grade score. ठीक है? So डेटा हमारे पास है, लेबल्ड वहाँ पर डेटा है कि प्रीवियस हमारे पास कुछ स्टूडेंट्स का रिकॉर्ड था और उस स्टूडेंट का ग्रेड क्या आया था वो हमारे पास है. So this is why we call this labeled. And of course, इसके कितने डेटा सेट्स हैं? That is 1 to n, let's say. So this is our training data. Okay, so we have information about some students, whatever their features are, and what grade they got in a particular course. Let's say this information is for students in the previous semester. Now I want to build a model on this and use it for students on this semester and predict what grade they will get in the course this semester. Okay? So the general setting here is X is a representation for a student, usually a vectorial representation, and it is, of course, an object. This X basically comes from the set of all possible X's. Okay? So capital X. So you can think of capital X is the set, is the population of all students. Okay? All students that are possibly can take these courses. Okay? And similarly, Y, which is the label, in this case is grade, okay, comes from the set of all possible grades. And let's say this is our set A, B, C, D, E, sorry, and F. So 5 possible values. Okay? So there are 5 possible values in the output, and these are labels. Of course, मैंने यहाँ A, B, C, D लिखा हुआ because we know that these are grades, and we can understand what A means, what B means, but you can give them any other labels as long as you can interpret those labels. So whatever encoding we use for those labels is not important. Okay? So this is basically our problem setting then. You have a data set of X and Y, which is all our examples, and X belongs to, from a mathematical perspective, from all possible students who can take a course, and Y can take on a value from the set of grades. So given this, we want to learn a mapping function. I shouldn't say in general a function, it's some model F, okay, or some procedure F, which can map any X from the possible set of X's to a Y from the possible set of Y. Okay? So in other words, our task is to learn F. So F basically you can say is a model or structure, or you can say procedure, which, so once you have this procedure, let's say you have learned this, so you already have F. Then when you give F some new X, it will tell you its corresponding Y. Okay? So that is our prediction then, after we have learned this F. Okay, so this is the general setting of a classification problem. We are given training data set which are labeled examples. We have the object in some representation, usually a vectorial representation X. And for that object, we have the label also Y. So X in general is a vector, Y in general would be a scalar. Okay? A categorical variable Y, because it can take on maybe 2 or more values. So given that, we want to learn some model F which can do the mapping from any X, from the possible sets of X to a particular value of Y. So once we have learned that model, we can then use it to make predictions in future. So there is a learning step or a training step. Once we are done with it, we can forget about it. We have then use the model. The model is F. So model अब हमारे पास आ गया. उस model में जब भी हम X कोई डालेंगे, let's say X25 डाला, तो इसका corresponding Y मुझे मिल जाएगा. And this X that I put in there is in general not necessary that this X should be already seen. Actually, in reality, the best way to use a learned model is that it is applied on unseen examples that were not in the training data set. So remember the example मैंने क्या दिए थी, training data मेरा जो था students का X और Y का, ये last year का था, ठीक है ना? पर मैंने ये जो model बन गया, ये model मैंने इस साल के लिए चलाना है, इस साल के लिए apply करना. So अब जो मेरे पास X's होंगे, these would in general not be in my data set. And that is the best scenario for classification. ठीक है? So any questions so far? All right. So obviously classification is a very well studied area in machine learning as well as in data mining. And there are tons of techniques out there. We will briefly do a categorization and then talk about maybe 1 or 2 techniques only in this course. And one of those techniques would be decision trees and its variation like random forest. So first of all, let me just spend a little time on categorizing techniques. So the most common way of categorizing techniques for classification are based on the underlying, you can say, theory. What is the basis for the model? So based on that, you can say that you have probabilistic methods. Okay? So the underlying theory that goes into these methods is probability theory. Okay? And then we have another category called statistical methods. So in this, we don't really talk about probability explicitly. We talk about, you can say, data and frequency and statistics and maybe optimization. So explicitly, probability is not the factor in statistical methods. And I will give some examples shortly. And of course, within the statistical methods, of course, example बाद में भी दे दूंगा, neural networks. And then and okay, then the third one, which you may not find in many books, but I usually have this category as well, is called information theoretic information theoretic methods. So these methods are based on concepts on information theory. So probability uses probability theory, statistics focusing primarily on statistics and optimization, and information theory focusing on information theory. So just to give some examples of probabilistic methods में आपके पास क्या क्या आता है? You have the naive based classifier, ठीक है? We have logistic regression, ठीक है? We can also have the conditional random field, which is a probabilistic graphical model, and in general, graphical models are also probabilistic. And what else? And I'll also add within this category, of course, there are various categorizations, but I will also add within this category of probabilistic the technique called the K nearest neighbor classifier. So K nearest neighbor classifier is also a probabilistic classifier. Okay. So these are some of the probabilistic classifiers. What about statistical? So ISME, of course, nowadays very popular neural networks and various forms of neural networks. There are tons of neural networks out there. Okay. And previously also very popular was support vector machines. Okay. So these are also, you can say, statistical techniques for classification. And then information theoretic. Theoretic. So ISME, of course, we have the decision trees. So decision trees are actually information theoretic in nature. They are based on concepts from information theory. There are also many other ways of categorizing techniques for classification. I'll quickly mention those categories, but we won't go into the details. One very common way of categorizing, although I don't like that much, but you might see that in the literature, is what is known as non-parametric and parametric techniques or methods. Actually, almost all neural network, almost all classification techniques are parametric. So non-parametric, the term non-parametric in this categorization means something else, slightly something different. So of course, I won't go into that detail here, but it is sufficient to say that this categorization is only important for mostly probabilistic methods. So almost all statistical methods are parametric, you can say, and information theoretic methods usually don't have this distinction at all. They do have parameters, but हम इस तरह की distinction नहीं करते कि non-parametric है या parametric है. ठीक है? So that is one categorization. So another categorization that is done is sometimes called instance-based versus model-based. Okay? Methods. Model-based methods usually build an elaborate model from the training data, and they are distinct training and test or prediction phases. While in instance-based methods, usually we don't have a distinct training and test phase method or prediction phase method. There is only one procedure, and that procedure goes over the data and make the prediction. To separate training or there is no separate training that's done and then you stop and then you apply the model. In instance based, you have to run the model from scratch every time. So इसमें जो most important जो category है ना, of course, KNN classifier is instance based. Because this model, this classifier does not build an explicit model. So whenever you want to make a prediction, it goes over the entire training data, looks at it, and then makes a prediction. So you can say that in this case, you don't learn actually a model, you learn a procedure or you build a procedure. So that's why in the beginning I said F can be a procedure as well. Some structure, some regularity, some procedure. So these techniques actually also are called lazy classifiers, because they don't learn a model a priori and then use that model. So they just, जब भी आपको कोई prediction चाहिए उसी वक्त ही वो data को देखते हैं और then make a decision. ठीक है? So that was, I think, a bit of intro. What I plan to, as I said, cover is to cover decision trees. So if you like, I can also cover naive Bayes as well. But that's all up to you. I can also cover KNN if you want. But फिर वो ज़्यादा चीज़ें हो जाएंगी, देखते हैं क्या करना है हमने. But decision trees I was kind of motivated to cover in this course. Of course, naive Bayes or logistic regression or even maybe SVM and neural networks and KNN, I think you typically study in the machine learning course. Okay. So we have about 10-15 minutes, so let's get started. So as I said, decision trees are information theoretic classifiers. Okay? And they build a structure. The model is actually a structure which is a tree, as the name suggests, decision tree. And using that decision, once that tree is built, you can then use that tree to make future predictions. So let me see if I can. So basically, let's say you have 3 attributes, A, B, and C. Okay? So you can build a decision tree. Let's say ये A attribute है, 2 possible values थी. ये tree नीचे आ गया आपके पास, यहाँ आपके पास B था, इसकी भी let's say 2 possible values हैं. इधर आपके पास C था, इसकी भी 2 possible values हैं. You reach the leaf node. Here we have the decisions. At the leaf node, we have the decision. So this is the type of structure that is actually learned using a decision tree classification problem. And what this figure shows is that at the root, we check the attribute A, and let's say the attribute A has 2 possible values, or let's say मैं binary assume कर लेता हूँ for simplicity, or left 0 है, right 1 है. So if मेरा कोई नया instance की value 1 है, so I'll take the right path. And then if I go to the right path, and you notice that I have to check now C, because right node में जो decision आ रहा है नीचे वो C पे आ रहा है. Let's say इसी example का मैं C देखता हूँ और C मुझे पता चलता है वो 0 है. So I'll take the left path there. And then when I take the left path, I do not have any other decision. I reach the leaf node. So leaf node then actually has the label. So given this example, or this new example where we have A is equal to 1 and C is equal to 0, I reach a leaf node. Let's say वो उसका label, let's say जो भी था let's say positive था, let's say sentiment classification कर रहे हैं. So now I know that whenever I have a observation with A is equal to 1 and B is equal to C is equal to 0, the label for that would be positive. And similarly, you can traverse other paths from the root to the leaf to give you other labelings for the data. So now this was actually assuming you have already learned this. Now the question was, how do you learn this structure? So that is the whole idea of decision tree learning. So let's look at this. So as before, we have xi, yi, I is equal to 1 to n. X, of course, is the representation for an observation, an object. Y is the corresponding label, as we had discussed before. So here, first, we will assume that X has discrete attributes only. Okay? Meaning that X is the object is described by discrete attributes only or categorical attributes only. So each attribute may have different number of distinct values, but they are still discrete. So for example, हमने जो student की बात की थी, so let's say you have an attribute gender. Gender obviously has two possible values, male and female. And let's say you have some other attribute, let's say उसका क्या कहते हैं what do you call that? आपका जो फर्स्ट ईयर, सेकंड ईयर, थर्ड ईयर जो होता है उसको क्या कहते हैं? Whatever, standing कह लें, I've forgotten the name. So let's say standing in this would be, of course, freshman, junior, sophomore, and of course senior. ठीक है ना, चार possible values and so on. So we have attributes like these which have discrete, distinct possible values, finite, distinct possible values. ठीक है? So, and of course, you will have multiple attributes describing your observation. So let's say in all you have m attributes. Okay? So you have m attributes. M, of course, would be generally greater than a dozen. Otherwise, of course, your problem will become very trivial. Okay? So now, as you saw in the tree before, आपके पास एक decision हो रहा है at a node. Now the question arises is, how do you decide which decision or which attribute on which attribute to select to make the decision? So that is the main crux of the decision tree learning algorithm. So we decide that by what is known as a splitting criterion. Okay? So this is some information theoretic measure that would tell us that this attribute is a good attribute upon which to split the data. Why do we call this splitting? Because if you remember, हमने जब A किया था तो एक साइड पे आप जा रहे थे 1, ठीक है, और दूसरे साइड पे आपके पास क्या था? 0 था, ठीक है ना, ये ट्री बन रहा था इस तरह का. So what does that mean? जो उसका ब्रांच बन रही है उसमें सारे वंस के डेटा सेट्स जा रहे हैं, वंस जा रहे हैं, जिनमें a is equal to 1 है. दूसरी तरफ आपके पास a is equal to 0 जा रहे हैं. So in other words, your data set is now split into two. One branch takes all the values with a is equal to 1. The other branch takes all the values a is equal to 0. ठीक है? And of course, we would like to do this split such that we are better able to discriminate the final classification of our data set, which is based on the value of y. ठीक है ना? ठीक है? And then of course, जब एक split किया तो you do the split recursively at the lower level. So in that sense, the algorithm, I mean, if you talk about from a purely algorithmic perspective, it is kind of greedy. Greedy because जो भी आपने information splitting criterion use किया है, greedily जो भी best है वो आपने select कर लिया. And then of course the other characteristic is it's kind of a divide and conquer recursive approach. ठीक है? So you repeat the step, repeat the process at each path as you move from the root to the leaf node. ठीक है? So 6 or 7 हो गया. I think the majors हैं वो probably फिर मैं next class में start करूँगा. So are there any questions so far? So we do have a quiz in the next lecture on Monday at the end of the lecture. Okay. So we'll be continuing with our discussion on decision trees in the next lecture. And I think probably we'll finish it in the next lecture. And then if we want to talk about any other classifier briefly, we'll do that in the following lecture. And then we will see कि हमने क्या करना है. I wanted to talk a little bit about spatial temporal data mining. And let's see. Although आज आपकी email भी आ गई है, Provost is kind of recommending that we stop after, give you one more week off. So let's see what to decide. So are there any questions?
सर ये स्प्लिटिंग डिसीजन ट्री में हमेशा 2 पे ही होती है या मल्टीपल स्प्लिट्स भी बन सकते हैं?
नहीं, मल्टीपल भी हो सकते हैं. सो फॉर एग्जांपल जैसे मैंने जो दूसरा एट्रीब्यूट बताया था स्टैंडिंग ऑफ ए स्टूडेंट or the rank of the student, so that would be 4 possible splits because उसके 4 possible values. Number of splits would always be equal to the number of possible values for that particular attribute. ठीक है?
Okay.
Any other question? So we will talk about the basic decision tree, talk about things like entropy, information gain, gain ratio, Gini index. We'll also briefly talk about pruning. And then maybe I'll talk about the idea of random forests and extreme random trees, which is very similar, but those are also quite popular in modern day. So this would most likely be in the next lecture.